Hello there. In this video, I want to talk about this paper, a ConvNet for 2020s. This paper is published by Facebook Research and it is available from 10 January 2022. Basically, this paper is talking about what is the state of the convolutional neural network. Is the inductive biases coming from the convolutional neural network is comparable with the transformers or not at all? So there is a picture, figure 1 of this paper, showing that the ResNet is one of the convolutional neural network which could gain the state-of-the-art performance on ImageNet, on ImageNet 1000. And after that time, so there are different state-of-the-art approaches based on the transformers. One of them is DEIT, another is a Swin Transformer, and basically this paper is not devising anything new, but it's just summarizing what happened to the convolutional neural network, especially to the residual neural network, and which is the new version of it can be called ConvNeXt. And there are some sort of engineering that happened inside the convolutional neural network that could gain the performance and also the flops gain the performance speed. And for having a larger data set training size, again, comparing to Swin Transformer, which is now one of the state-of-the-art for many tasks to be a backbone, like for example, in segmentation or object detection. So ConvNeXt are showing comparable results. The paper starts with these sentences that roaring 20s of visual recognition began with the introduction of vision transformers. And they quickly superseded ConvNets as the state-of-the-art image classification. However, vanilla vision transformer faces difficulty when applied to general computer vision tasks such as object detection and semantic segmentation. And therefore, the Swin transformer is announced, which is the hierarchical transformer, and it could show that the transformers can practically viable as a generic vision backbone and demonstrating remarkable performance on a wide variety of vision tasks. So there is an interesting sentence here. They mention the effectiveness of such a hybrid approach is still largely credited to intrinsic of superiority of transformers rather than the inherent inductive biases of convolution. So in ViT, we usually have patching of the images, then we may or not apply some convolution and then apply to the transformer. And they're mentioning that the most of the performance gain coming from these versions like DIT, VIT is coming from the transformer inductive biases. But what happened to the that branch of deep learning that we were following about convolution? Are they useless, or we can improve them somehow? We can change the architecture somehow to gain again the performance of the state of the art. So they mentioned here in this paper, we re-examine the design space and test the limits of what a pure ConvNet can achieve and gradually modernize the standard ResNet toward design of a vision transformer. So basically, if I come down, I don't want to go through the introduction and what's happening to the ResNet, what other people were doing to make convolutional neural network more practical. So this is a map here, chronological map that they're showing. There are different kind of changes we can apply on the architecture of residual neural network. And if you have residual neural network and its counterpart, Swin Tiny, and if you want to compare residual neural network 200, ResNet 200, with Swin base, that would be a fair comparison because the complexity of these two models are same. That's why in the whole paper, it's categorizing these two different networks in this way. So if you have ResNet 50, we can apply macro design changes, ResNeXt introduction, then we have inverted bottleneck part, and large kernel experiments and micro design in contrast with macro design. And then we can reach from ResNet 50 to ConvNeXt, and you can see the accuracy can increase from 78.8 to 82 and also even outperform the Swin Transformer, tiny. So in this paper, they're walking through all of these steps from macro design to micro design, and they're talking about all of these stages, what's happening there. So I just walk through each of them very fast, and also we will look at the code to see how we can use it, how we can use ConvNeXt in our code. So the first thing is macro design, and is changing the stage compute ratio. So mainly they are saying that the Swin Transformer are using this kind of stages. For example, they have one block, then 9 block, and 1 block. And previously in ResNet, we were using something like 3, 4, 6 tree. And one of the changes to match with the Swin Transformer architecture is to change that ResNet 50 to something like this. So it's somehow the multiplication is somehow valid because, for example, it's mentioned here the Swin Transformer ratio is like following multiplication by 3, so it's somehow valid. And they mentioned by just changing this, they could gain improvement from 78.8 to 79.4. So also each of these steps are not drastically changing the performance, but putting these steps all together in one network can gain the drastic change. So another part is changing stem to patchify. So the stem of the residual neural network, it's mentioned here, was 7x7 convolution layer with stride 2, and followed by a max pool, which result in a 4 by downsampling of the input image. And they replaced that stem cell using a 4x4 stride 4 convolution layer. And this is again getting the idea from the Swin Transformer, because the patchifying 4x4 that is happening inside the Swin tiny transformer, for example, in ViT model or in DIT model. So they're using same 4x4 non-overlapping patchifying images. So this stem layer is used, and it could gain improvement performance of 0.1. The next changes is ResNeXt. So we finished, I go back here. So we finished macro design, the stage ratio, and the patchifying stem. So now we are in the depth convolution and increasing the width. So another changes they made is to improve the performance speed of the ResNet. There are some models, there are some architectures that apply the convolution on depth-wise other than spatial dimension. And also another thing is that ResNeXt employed grouped convolution for the 3x3 convolution layer in the bottleneck block. So instead of having just one convolution, we have a group of convolution. And basically, in the ResNeXt, the number of group is usually same as the number of dimension of images. And the next thing is inverted bottleneck. There is a paper, it's called Inverted Bottlenecks and Inverted Bottleneck Block, I guess. It is related to the improving the ResNet performance by replacing the convolution layer with the multi-head self-attention. But this is different. They are saying that instead of this is a linear layer and this is convolution layer. And they are mentioning that if we have linear layer and a convolution and linear, one of the ways that we can invert these values just to reduce the number of multiplication, and also it's called inverted block. They're mentioning the position of a spatial depth-wise convolution layer is moved up. So because we are applying on the depth-wise, this is introduced in MobileNet version 2, so we can change these two layers, decrease number of flops, and apply the convolution on depth instead of in the spatial dimension. And we can improve the performance in some cases, and at least remain in the same performance by decreasing the flops a lot. And MobileNet is basically, from the name, you can guess that it's coming from architecture that can be used inside the mobile devices that have less computational power. So the next thing is the larger kernel size. So they are mentioning here, instead of 3 by 3 kernel, they could use 7 by 7 to explore larger kernels. One prerequisite is move up the position of the depth-wise convolutional layer. So as I mentioned here, if they want to use larger kernel sizes, it's better to have it on the top. The complex inefficient module, multi-self attention or large kernel convolution will have fewer channels, while the efficient dense one by one layers will do the heavily lifting. This intermediate step reduced the flop to 4.1, resulting in temporary performance degradation to 79.9. So these changes, as I said, it's not always gaining the performance, but it's reducing number of flops. And they are mentioning when they do these kind of changes, they can increase kernel size and again regain the performance. So from 79 to 0.9, it could the neural network performance can get 80.6 by 7 by 7 kernel size. And then at the end, we have micro design. The micro design is changing the ReLU to GLU. The GLU is the Gaussian error linear unit here. And changing ReLU to GLU is just done because in many transformers, like in Google BERT, in OpenAI GPT-2, and most recently in ViT, the GLU is used. And there is no performance gain here, but because it showed a good performance and also it somehow have a better and a smoother variant and trajectory than ReLU. So it is better in the training and smoothing the loss trajectory. So another thing is reducing the activation layers. So if you compare this one, you see the differences. For example, in Swin Transformer, we don't have lots of activation layers here, but in ResNet, for example, we have batch normalization, another batch normalization, another batch normalization. So some of these are redundant. They did some experiment and found that instead of batch normalization, we can use layer normalization. So I have another video, you can go through that. It is micro batch normalization and weight standardization. They mentioned here that instead of batch normalization, they can use layer normalization and also removing this one because this one didn't affect on the result. And so therefore, we only have one layer normalization and that doesn't have any activation function here. And only activation function is after this linear layer. That linear layer also can be, in the implementation of the Facebook research, it is linear layer, but it can be also a convolution one by one. So, so they are mentioning here again, substituting the batch normalization with layer normalization could improve the performance, and also using fewer normalization also could improve the performance because we are reducing some of the parameters of the system. Another part is separating down sampling layers. So they are mentioning that before going to each of these blocks, we can have a down sampling layers because in Swin Transformer, we have the same down sampling layer. They use 2 by 2 convolution layer with SRI 2 for a special down sampling. And this is applied before any stages, just once before any stages. And that's it. This is the ConvNeXt, and let's see what is the result just by applying these steps, what happened to the system. So they are showing the performance of the classification of top 1 accuracy on ImageNet 1000. And also in the down here, they are showing the performance of the object detection and the segmentation. So you see that the performance of the models, like, for example, if you see the average precision of the mask and average precision of the box, so you see the performance of ConvNeXt is outperforming the Swin Transformers, their counterparts, the large ones and the base ones and small ones. So the paper is not claiming that the convolutional neural network is better and outperforming transformer, and transformer is not good. It's mentioning that the convolutional neural network features, the inductive biases coming from them is useful. And sometimes we just need to use some engineering. Maybe this kind of engineering, if it is happen on the Swin transformer to design them better, and they can even outperform the current metrics that they have. By the way, at the end of the paper, they're also showing some of the parameters that they used during the training. And also, they were showing that the complexity of the ResNeXt model is less than the transformers, so it's maybe better for the production. For example, you can see the throughput of image per second for a ConvNeXt in all of the versions are better than the Swin models. So if we search on the Google for ConvNeXt, we will see the Facebook research ConvNeXt. I just want to walk through. You can see different kind of things. Like for example, they used detection library, and there are some backbones for using the ConvNeXt in the detection, stuff like that. And the main thing is that we should see, for example, the ConvNeXt, the main ConvNeXt model here. You will see that there is a ConvNeXt. It is implemented in Torch, and we have number of channel, number of classes, and basically we have the stem layer. And for stem layer, we have three times repetition of that stem layer. The first one is, for example, the dimension first is 96. So we have number of channels. For example, this is an RGB image, would be 3 to 96, and then we have a layer normalization, and we append 3 other downsampling layers. So this would be just downsampling layers. Then we will have the main block. So this downsampling layers is talked inside the paper as the last step, if you remember. Then we have the block. Each block is the ResNeXt. Basically, in the forward function, we have first downsampling, then we apply the block, and each block maybe has different dimension as we talked about. And for example, if you want to have ConvNeXt tiny, so we can say the depth would be 3393, and dimension we will have. So if we come back up here, so we are getting the depth, and that depth here is getting be used for creating different blocks. For one stage, we will have, for example, 3, then in the next stage we will have another 3, then in the next step we will have 9, and the next stage we will have another 3 blocks of the ResNeXt. Each ResNeXt starting with a downsampling layer. At the end, also we will have a layer normalization and the linear as the classification. So going up to see what is the block. So the block is the first is the convolution layer. So we have dimension, for example, is 96 to 96 with kernel size 7. And then we have layer normalization. You can remember that figure I showed you, the comparison between ResNet and the ResNeXt or ConvNeXt. And then we have linear layer. So as I said, it can be also the convolution on one dimension, I guess. And then we have the GELU, another linear layer, and that's it. So we have the dropout. This is something specific. The dropout is not same as the the drop pass is not same as the dropout. So the drop pass is just ignoring one of the samples. It's dropping one of the whole samples. And yeah, put a comment if you know about that specifically. I can make a video about it. It is currently in the team image processing module. And after forwarding that block, because this is a residual, we get the output of X, and we drop one of the sample, and we add it to the first input of the network. So that's the residual connection that we have. Also, there is another point. They're mentioning we can have 2 approaches. Both are same, but one is just usually in PyTorch, we have number of channels at the second, which is not good because there are some articles on the internet and papers. They're talking about that if you put the number of channels at last, the performance speed can improve a little. So I think they use the second one just to move this to the last and then return it back. And they are mentioning that part here. So that's it. I hope you enjoyed the video. Please put a comment, share video with your friends, and subscribe. 90% of the people that watch these videos are not subscribing. I appreciate your support. Thank you.